Okay, our last section in Module 5 is about rational functions. Now, rational functions is just really a rational expression that's going to be equal to a different variable. So it's going to be a function in the form where we have y, which is some variable, equal to the quotient of two polynomials. So you have a polynomial on top, a polynomial on bottom, but you have a y equals for it. So for example, y equals x plus 2 over x. That would be a polynomial function. We can also write it in the function notation with f of x equal to x plus 2 over x. Now the interesting thing about the graph of a rational function, which we can always graph on Desmos, is that all the rational functions don't look the same. For quadratics, they all look like parabolas. For a linear function, they all look like lines. Rational functions, they all have kind of a distinct view for each one, but there are some different parts that we can learn from and kind of help us to understand what the graph looks like. The first one is what's called a vertical asymptote. Now, a vertical asymptote is going to be a vertical line that the graph approaches but does not touch. But the graph gets closer and closer and closer to this line, but it's never going to touch it. So if you look at the graph below I have, this is a graph of a rational function. Now if you look at the graph, which are these red lines, you can see that this part of the graph starts to go down and this part of the graph starts to go up. So if we imagine this vertical line here at x equals 3, then this is the line that the graph is getting very, very close to, but it's not touching. So this asymptote, this vertical asymptote, is where this thing breaks apart. So in this graph, we would say there is a vertical asymptote, or VA, at x equals 3. At least it appears to be that way. There is definitely an algebraic way to find these, where you can very easily find the vertical asymptote. So if you have the equation to algebraically find the vertical asymptote, just see what makes the bottom 0. When your function's in lowest term. So whatever makes your function equal to 0 when it's in lowest terms will be your vertical asymptote. So if you have an equation, it's sometimes easier than actually just looking at the graph. Not that the graph isn't helpful, but sometimes the equation will just show you what it is. Okay, so here are a couple examples. Here's a rational function. We want to know where does the rational functions have a vertical asymptote. We want to find our answer algebraically, and then we're going to graph it on Desmos to check. So this one is already factored. There's nothing to factor, so there's nothing I can cancel out. It is in simplest terms. So if I look at the bottom here, which is just x minus 4, I want to know when is x minus 4 equal to 0. Well, this is quite simple. We'll just add 4 to both sides, so x equals 4. Now if we would have had to factor and cancel, it may have been different, but in this case not. So 4 makes the bottom 0, so that's going to tell us that we have a vertical asymptote at x equals 4 for this graph. So I've graphed it here below. Here is the graph. Now I'll show you some things on Desmos, how I put it in. If you notice, when I put this in Desmos, I have the parentheses around the top and the bottom. That's very important to make sure that you have these as distinct tops and bottoms. Now here's our graph over here. Now our algebra said that this should have a vertical asymptote at around 4. So if I look at the vertical line of 4, which is right here, that kind of agrees because that's where the graph breaks apart, and that is where I would say the graph is approaching but not touching. Okay, let's look at this next one. We have y equals 2x over x squared minus 25. Now this one certainly will factor because the bottom we know is the difference of squares, so x and x, 5 and 5. You also might have to do your rectangle factoring where we factor a trinomial. So this will factor as x minus 5x plus 5. Now nothing cancels out, so it's in lowest terms. So I'll take the two things that are on the bottom and I'll set those equal to 0. So in this case we're going to have two vertical asymptotes because we have two things that make the bottom 0. One of them would be 5, and one of them would be negative 5. So we have vertical asymptotes at x equal to 5 and x equal to negative 5. So if I look at my graph, which I've graphed here, 2x over x squared minus 25, notice the parentheses again. So you'll see that there appears to be two breaks in the graph. There's one here where this part goes up and this part goes down, and where this part goes up and this part goes down. So we have two vertical asymptotes, and you can see this looks totally different. It's got this kind of part of the graph here in the middle. It's got the two ends, which is similar to the other one, but just a little different. Okay, another kind of important part of a rational function is when you have holes. Now a hole is a single break in a graph. Okay? So if I have a graph, let's just say I have some graph here. If I come to a point and there is a hole in it, so a little singularity hole, then the graph keeps going, this is referred to as a hole. Okay? So you find holes by finding any factors that cancel. So any factor that cancels will create a hole. So if I look at this example, I want to know if the graph has a hole and if it has any vertical asymptotes. So we should always try to find the holes by canceling any common factors. So if I factor this one, we know the top is x minus 2. The bottom is x minus 2, x plus 2. This is the old difference of squares, x and x, 2 and 2. So you'll see that x minus 2 cancels out, leaving us with 1 over x plus 2. So because this x minus 2 factored out, we'll have a hole wherever that equals 0. So since x minus 2 equals 0, at 2, we have a hole at 2. Now, our simplified version here, since this is our simplified version, we can look at the bottom of that, and just like we did previous, this will find our vertical asymptote. But it's important to make sure you cancel out, like we did. So x plus 2, so subtract 2 from both sides, so x equals negative 2. So this has a vertical asymptote at x equal negative 2, and it has a hole at x equal 2. Now if you graph these, you will not really see holes because they're basically like a single little point. So if you look at a pixel on a computer screen, it's very hard to pick out maybe just one to match up right with our hole. But it is kind of a gap in the graph. Okay, let's look at our second one. So we have 2x squared minus 50 over x plus 5. So the bottom is not going to factor. But the top I can factor. I could first take a 2 out because they are both divisible by 2, so I could take that GCF out. And then we have our difference of squares again. We've done this factoring before in this video. So x minus 4, x plus minus 5, and x plus 5 over x plus 5. So you'll notice we cancel the x plus 5 out. So anytime we cancel something out, we'll have a whole. So whole is going to be where x plus 5 equals 0. Subtracting 5, x is going to equal negative 5. So there's our whole. Now when I cross that out, you'll notice I have x, or 2 times x minus 5. There's no denominator anymore except for 1. So there's actually no vertical asymptote. Because there's nothing in simplest form for the bottom to be equal to 0, so there's just not going to be one. Okay, the last part of the graph we're going to look at is a horizontal or slant asymptote. Now, horizontal or slant asymptote is going to be either a horizontal or slanted line the graph approaches as the absolute value of x gets very large. That's kind of a fancy way of saying what happens to the graph as it gets very far to the right and very far to the left. So you can have your graph and it could be doing something, but if it goes off and it kind of starts to follow a slanted line pattern, then that's a slant asymptote. Other graphs will kind of flatten out to be some line. So this would be a horizontal asymptote because you see kind of how it flattens out. Now we could find these algebraically as well. The problem is we have to go back and we have to use our concept of long division. Now the algebraic way we find these is first of all, if the degree of the bottom is greater than the top, we always have a horizontal asymptote at y equals 0. So if the degree of the bottom is bigger than the top, then we always are going to have a horizontal asymptote at y equals 0, no matter what. Now the problem is if that's not true. If not, we must long divide to find the horizontal or oblique or slant asymptote, sometimes also referred to as an oblique asymptote. So we'll have to kind of review how to do that. The good news is we don't have to do the full long division. We just have to long divide until we find our asymptote. So we don't have to find remainders or anything like that. We just kind of have to find what the asymptote is. So let's look at a couple examples. This first one is actually the easiest one, because if you look at the degree of the bottom, the highest power, it is 2. If you look at the degree of the top, it's only 1. So automatically, since the degree of the bottom is bigger than the top, so the degree of the bottom is greater than the degree of the top, we automatically know this has a horizontal asymptote of y equals 0. No fancy math, nothing else. The degree of the bottom is bigger than the top. You automatically have a horizontal asymptote of 0. Now let's go ahead and take a look at the graph of this. So I graphed it here. And what you'll notice here about this having this asymptote at 0, if I put a horizontal line through 0, you should notice how this graph will start to approach it. This part of the graph here starts to get very, very close to it on this side. And over here, this part of the graph is getting very, very close to it on this side. So no algebra in that one though, so that was kind of nice. Okay, now this one, the degree on the bottom is not bigger. It's actually the same because we have one on the bottom and one on the top. So to find the asymptote, we will have to divide. So you always take the bottom outside and the top on the inside. Now I'm only going to divide until I see a constant number on top, then I can stop. So sometimes it might be 1 step, sometimes it might be 2, but it'll never be more than 2. So if I look at the first numbers, I have 2x on the inside and x on the outside. I will divide those. So 2x divided by x equals 2. So I put a 2 on top. Now we would normally multiply this around and stuff, but I don't have to. We can stop here because I found a number. Once I get to a number on the top, I am done. So this has a horizontal asymptote of y equals 2, because that's what my value is. So right away, I'm done. So if I look at my graph of this, which I put into Desmos, you can see here's 2, here's the line y equals 2, which is what we found algebraically to be our horizontal asymptote, and you can see how this graph is getting pretty close to that. Okay, let's look at one more. So we have y equals x squared minus 3x plus 1 over x minus 4. Now in this case, the degree of the top is actually bigger than the bottom. So I will divide these, and we're going to have to do a couple steps here. So again, we take the first term in the outside and the inside, and we divide. So x squared divided by x, well, we'll cancel on x, so we're just left with x. So the problem is we have to keep going in this case. So we'll multiply the x to both these things out front. So x times x is x squared. X times negative 4 is negative 4x. So we change the signs, and that's the key thing. Once you multiply it around, you subtract, which changes the signs. This one to minus, this one to plus. So these cancel out. Negative 3x plus 4x is 1x plus 1 when I bring that down. I won't need that bring down part though, because you'll notice now I'll take this x on the outside and this x on the inside, and I'll divide those. So 1x divided by x is going to be 1. So I put my 1 there and I stop, because all I have to do is go until I get a constant. Now my asymptote is going to be y equals x plus 1. Well, that is a slanted line. So I have a slant asymptote of y equals x plus 1. So if you look at our graph, this graph, as it gets very big or very small and goes off the ends of the pages, it should approach this line y equals x plus 1. So if I plot that line, here is 1, up 1 over 1 looks something like this. So if I graph that line, you'll see that these red lines actually do approach that slanted asymptote. So it's just what happens as you go off the page. Where is this graph going? Okay, let's look at one where we put it all together. So we have y equals x minus 7 over x squared plus 1. So I can factor this. So I know this is x minus 7 x plus 1, x minus 1. So I know this has no holes. The reason I know it has no holes is nothing cancels out. So let's write that so you have that for your notes. And of course we could graph this on Desmos and see some of this, but it's hard to see the holes. It has two vertical asymptotes. It has a vertical asymptote at x equal 1 and x equal negative 1. Because you can see there are two bottoms here, so if I take x plus 1 and set it equal to 0, x minus 1 set it equal to 0, I'll get 1 and negative 1. So I'm just going to kind of draw those asymptotes on the graph. And these won't actually show up if you do it on Desmos or anything, but it's just kind of a nice guide to kind of see where your graph is going. I also know its horizontal asymptote without doing much work. The horizontal asymptote is y equals 0. Because if you notice my graph, the degree of, or my equation, the degree of the bottom is bigger than the degree of the top. So automatically it's equal to 0. So I know the graph is going to kind of approach this line as we go off the page. Okay? Now beyond this, we don't have a lot of other tools to do these right at our disposal right now. There are a lot of techniques from calculus and stuff that you could graph these, but since we are not doing that, we'll just kind of graph it in Desmos and kind of fill in the rest. Okay, I graphed it on Desmos. Now you got to be careful because this one's a little high. You might have to zoom out a little bit. But what it looks like is I'll see that there's a little parabola part in the middle, so something like this. It's going to go between those asymptotes because it can't cross it. And then we'll have two parts that kind of come up like this. But you can see the general part of the graph from its Desmos part. But we got the asymptotes, so we know a lot of things about the graph just from its equation. All right, go ahead and try your last section of our module. And let me know if you have any questions.